Alright guys, so in this video we're going to continue talking about colligative properties, specifically freezing point depression and boiling point elevation. So remember that colligative properties depend on the number of particles dissolved in solution. So that directly relates to your concentration and your Van Hoff factor, I. But it does not depend on the type of particle. So if we look at a phase diagram for a non-volatile solute, we can see that the phase diagram shows temperature on the x-axis, pressure on the y-axis, and it shows the phases from solid, liquid, and gas. And at 1 atmosphere is where we find the normal melting point of the solvent going from solid to liquid, and the normal boiling point of the solvent going from liquid to gas. And so we can see that when we have a solution, which is indicated by the red line, the solution is actually shifted lower in vapor pressure at all temperatures. And this downward shift in vapor pressure directly leads to a change in the melting point of the solution and the boiling point of the solution in comparison to this pure solvent. And so the change in the melting point of the solvent, pure solvent, to the solution is called the freezing point depression. And the reason that we call it freezing point depression is because there is a decrease in the melting point. We can also see that comparing the boiling point of the pure solvent to the boiling point of the solution, there is an increase. And so we call this the boiling point elevation. And so that word elevation, meaning that there is an increase in the boiling point as you add solute to a pure solvent, forming a solution. And so antifreeze is an example of a real-world application of freezing point depression, because antifreeze is actually a solution of ethylene glycol, and pure water. So if we were to just put pure water into our car, well, at lower temperatures, this would cause the pure water to freeze and therefore expand, causing your pipes to bust. So by using a solution of ethylene glycol and water, that would lower the freezing point in order for this solution to stay liquid and not bust the pipes in our cars. And so freezing point depression is designated as delta T sub F, and it's equal to I times M times Kf. Now I is equal to Van Hoff factor of your solute, M is the molality of the solution, and Kf is the freezing point depression constant for the pure solvent. So if we take a look at these variables, we can see that I is dependent on whether the solute is an electrolyte or a non-electrolyte. M is showing that concentration directly relates to the change in freezing point depression, and the freezing point depression shows that the solvent in which the solute is dissolved is important in determining the final freezing point of the solution. And so if we take a look at the units of these variables, we can see that the change in freezing point is in degrees Celsius, I is a unitless factor, M is in molality, which is moles of solute per kilograms of solvent, and Kf, the freezing point depression constant, is in degrees Celsius per molality. And so we can see that these molalities cancel out, and we're ending up with just this degrees Celsius, so the change in temperature. And so ultimately, to get the final freezing temperature of the solution, we need to subtract this change in the freezing point from the initial freezing point of the solvent. And so that's why we call it freezing point depression, because the freezing point is decreasing. And so you will be given the Kf values for the different solvents, and you should be given the normal freezing points of different solvents. However, you should probably know that water has a normal freezing point at 0 degrees Celsius. And so again, by taking an approach in which we're looking at a real-world application of this freezing point depression, we can take wood frogs, for instance. So wood frogs have this remarkable mechanism in which they're able to survive very cold winters. And the way that they do this is by releasing glucose into their bloodstream. So initially our cells just have a certain amount of water in them. If this pure solvent, water, was at a temperature of 0 degrees Celsius or lower, then it would freeze and cause the cells to burst. However, these wood frogs, when they release the glucose into their system, they're actually lowering the freezing point, which actually enables them to survive at temperatures as low as 8 degrees Celsius. So in this problem, we're going to calculate the molality of the glucose solution that's required to lower the freezing point of water to negative 8.0 degrees Celsius. So ultimately, we're going to see the concentration of glucose that these wood frogs emit into their bloodstream. And so in order to do this, we're going to need to use the equation delta T sub F is equal to Im times Kf. Remember, I for a glucose solution, which is a non-electrolyte, is just going to be 1. Our Kf value is going to be the Kf value of our solvent water, which is 1.86 degrees Celsius per molality. We're going to solve for molality in this case. Now, our delta Tf in this case, in order to solve for this value, we know that the freezing point of water in its pure solvent state is 0.00 degrees Celsius. And so ultimately, to get the temperature of the solution down to negative 0.08 degrees Celsius, we can solve for the delta Tf, which we can see will ultimately just be a change of 8.0 degrees Celsius. And so we can plug this information back into the equation, and so ultimately we can divide by the Kf value on both sides, and we ultimately get the molality of the glucose solution in the frog's blood, or in their cells, to be 4.3. So as we saw previously, boiling point actually increases, so it elevates in a solution in comparison to its pure solvent. So again, our variables here are delta T sub B, which is going to be the change in the boiling point, is equal to I, which is the Van Hoff factor again, our molality of the solution, and our K sub B, which is the boiling point elevation constant. So you can see that this equation is very similar to the freezing point depression, the only difference being that we're going to have a different value for this constant. So we take a look at the units of these variables, and we can see that the units are the same as they are in the freezing point depression. Molality cancels, and our change in temperature is in degrees Celsius. Now, a difference here in the equation is that our boiling point of the solution is going to be equal to the boiling point of the solvent plus the change in the boiling point. So we're going to be adding this change because we saw that boiling point increases upon the addition of solute. And so again, we're going to be given this constant Kb value. You'll be given the normal boiling point for certain solvents, but you should know the normal boiling point of water is 100 degrees Celsius. And so applying this idea of boiling point elevation, we ask the question, well, which solution has the largest boiling point? And so if all of these solutions are dissolved in the same solvent, which in this case is water, or it could really be any other solvent, but we'll assume it's water in this case, That means that our Kf value is constant. And if you look at the molality, the concentrations of all of these solutions, those are also constant. And if you recall the equation, delta T sub B is equal to I times M times the case, and I said K sub F, I meant to say K sub B because we're talking about boiling point. If we consider this equation, well, if these two variables remain constant, the only thing dependent on the change in the boiling point here is going to be our I value, so that Van Hoff factor. So we look at the solute that we're adding. In this case, it's sucrose, which is a non-electrolyte. So that means I is going to be equal to 1 because it's not breaking up in solution. However, if we add sodium chloride, this is a strong electrolyte which breaks up into two ions. It breaks up into Na plus and Cl minus. So our I value is 2 here. If we look at MgCl, which is a strong electrolyte as well, we get an I value to be equal to, well, let's see, well, we have 1 magnesium ion in solution and we have 2 chloride ions in solution, so ultimately we have a value of 3. So which solution has the highest boiling point? That's going to be our magnesium chloride because it's directly related to our highest I value.